Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to finish going through Chapter 3.6, discussing basis and dimension of vector spaces. In this video, let's jump to page 44 of your guided lecture notes and look at function spaces. A set of functions are linearly independent if and only if the only solution to this equation is the trivial solution where all of the c's are equal to 0. If the function is n minus 1 times differentiable on an interval I, then we can use the Wronskian to determine linear independence. The Wronskian is created by looking at a matrix where the first row of the matrix is your functions, the second row is the first derivative of your functions, and goes all the way up to the n minus 1 derivative, or the nth derivative. I think I actually say it's just say n minus 1 as an exponent there. The nth minus 1 derivative is what it should say. If the Wronskian is not equal 0, then the functions are going to be linearly independent. However, if the Wronskian is equal to 0, it does not imply dependence. If the Wronskian is ever equal to 0, in this scenario, we must actually use a different test. We will say the Wronskian is inconclusive. Must use another test. So let's look at some examples. Are the set of functions that are given linearly independent? And let's look at just this first one. Are these two functions independent? Now, there's lots of ways that we can approach this, but here we want to practice the Wronskian. So here we would be saying the Wronskian of e to the t, e to the negative t, is going to be calculated using a matrix where the first row are the given vectors, and the second row is the first derivative. Now we look at the determinant, the product of the main diagonal minus the product of the off diagonal. So here our main diagonal would be e to the t times negative e to the negative t, minus the product of our off diagonal, which is e to the t times e to the negative t. Now, using rules of exponents, we know that when we multiply exponential functions that have a common base, we add the exponents. So negative e to the t minus e to the t minus t, which is going to be negative e to the 0 minus e to the 0, or negative 1 minus 1 is negative 2. Notice that the Wronskian is not 0. So we could say the functions are linearly independent. Now, I said there's other ways we could have done this, but we were asked to use the Wronskian. Here, other ways that we could have done this is we could have said, let's let v1 equal the vector e to the t, and v2 equal the vector e to the negative t. And notice that v2 is never some multiple of v1 for any c. E to the negative t is not a constant multiple of e to the t. That tells me that they are linearly independent. Okay, let's look at another example. Are cosine and sine linearly independent? And here again, I would like to use the Wronskian. So here the Wronskian of cosine of t, sine of t. It's going to be a determinant of a matrix created by making the first row be our original functions. The second row is the derivative of those functions. And because it's a determinant of a 2 by 2 matrix, we take the determinant by looking at the product of the main diagonal minus the product of the off diagonal. So here we're going to have cosine of, or cosine times cosine would be cosine squared of t minus the off diagonal will be negative sine squared of t, which is the same as cosine squared of t plus sine squared of t, which we know is 1 by our Pythagorean identity. And because it's not 0, we can say the vectors are linearly independent. But again, we should have already known that sine of t is not a constant multiple of cosine. Remember when we did this before, if I gave you the vectors 1, 2, and 2, 4, then here we could say vector 2 is 2 times vector 1. That's how we said these are not linearly independent. So these are not, that's how we said these ones are linearly independent. But ours are not constant multiples. They're not linearly dependent. They are linearly independent. Okay, now the strength of this Wronskian could be seen when you look at determinants of more complicated functions, or when you look at whether these more complicated functions are linearly independent or not. So here's a set of 3 functions. We are asking, are these functions linearly independent? So our approach to this one is going to look at the Wronskian. So we'll look at the Wronskian of these 3 functions. As a determinant created by the first row being the given functions. And space these out a little bit so they don't get squished together. The second row is the derivative of these functions. The third row is the second derivative. And now we've created a 3 by 3 matrix that we want to find the determinant of. I'm going to use the cofactor expansion technique. And also I need to recall the signs matrix. Remember, we're doing the cofactor expansion technique. It does not matter which row or column you expand upon. However, you generally want to use rows or column that involves zeros. So I'm going to choose to expand on this third row. When you're expanding on the third row, you're on this first element, the 4. That'll be 4 times a smaller determinant created by canceling this first column, leaving a 2 by 2 matrix. Notice that the sign of this 4 is going to be positive. Then the next one's going to be minus. So minus 2 times the determinant created when you cancel that middle column. Plus 0 times the determinant, and I'm just going to say some stuff here. Because it really doesn't matter what's inside there, because I know the coefficient is 0, so this entire term is going to be 0. So now let's take the determinants of these 2 by 2 matrices, and because they're 2 by 2 matrices, we can use the product of the main diagonal minus the off diagonal. So it'd be t squared minus 1 times 1 minus the off diagonal 2t times t plus 3 minus 2 times, again, it's a 2 by 2 determinant, so the product of the main diagonal minus the off diagonal. Now we're going to want to simplify our expression some. I'm going to do some side work here. If I multiply this expression here out, I think it's going to be 4t times t is 4t squared, which means minus. 4t times 3 is going to be 12t minus t is 11t, but minus. And then negative 1 times 3 is negative 3, but times this would be plus 3. So I think we get here minus 2 times 2t squared minus t minus 5 minus 4t squared minus 11t plus 3. A little bit of algebra in this problem. Maybe combine some similar terms. So the t squared and the negative 2t squared would be negative t squared minus 6t minus 1. In our second grouping, let's again combine similar terms. So the 2t squared and the negative 4t squared. Negative 2t squared. Let's combine our t's, our would be negative t, and negative 11t is minus 12t. And then our constant terms, minus 2. Then let's distribute the 4 into the first grouping to get negative 4t squared minus 24t minus 4. And we'll distribute the 2 into our second grouping. Be plus 4t squared plus 24t plus 4. I think what we should notice is that all these terms cancel out and we get 0. This tells us that the Wronskian is inconclusive. Or that we need to try a different test. However, we should recognize this as a previous example. Where we showed these vectors are linearly dependent. And because they're linearly independent, they are not a basis for P3. Okay. This completes all the examples I wanted to do for chapter 3.6. I hope this gives you enough information to work on your homework for chapter 3.6. However, I'd be happy to do a couple more examples when we meet for our virtual class session. I hope this is helpful, and I'll see you next time.